topic for today's video is total internal reflection, and we're going to look and see what that exactly is. And we've also got some higher tier content to cover as well, and I'll point that out when we get to it. Now, the best way to demonstrate what we mean by total internal reflection is to do an experiment that might look a bit like this. You may have done this in class, but what we have is a semicircular glass prism, and we have a ray of light which is being shone into this glass prism, and the ray of light comes out the other side, but it changes direction a little bit. We say it refracts. Now, the angle at which it hits this little interface between the glass and the air, we call that the angle of incidence, and the angle at which it changes direction, the refraction angle, we call that the angle of refraction. We also have another line here called the normal line. This is an imaginary line, and I've drawn it as a dotted line here, but this is a line that's at 90 degrees to our glass air interface. So what we have is a light ray traveling into this glass prism, refracting slightly and coming out at the other end. But that's not the end of it, because what we also have is another ray of light, which is where the light ray here has reflected from the inside surface of the glass here. So we have a fainter line which I've drawn here. This is a little bit of reflection that happens, but we get mostly refraction and a little bit of reflection. It might be worth remembering also that this angle here which the light ray reflects is the same as the incident angle, and that's the law of reflection that we looked previously at in P1. This is not specifically required for this topic, so it's just a point that I'm just making as we're here. Now, what we could do next is we could increase this angle of incidence, so in other words increase the angle at which we're shining the light ray towards the glass prism, and what you would see is refraction would increase, and reflection would also, the angle of reflection would also increase. Let's just move the glass out of the way, and you would see something that looked like this. What I've missed out here, which is really important, is the arrow on the light ray. So that's the arrow there, but this is what you would see. I could increase this angle yet further, taking our arrow with us. I could increase it further, and you would see something that looked like this. Now, eventually you'd get to a point where you increase the angle of incidence to a point where the angle of refraction, the light ray, actually travels along the glass and air interface. So it would look like this. The light ray travels in, and the refracted ray travels exactly along the line as shown in the diagram. We have a special name for this angle. It's called the critical angle, and it's a very important angle because once we increase our angle of incidence above the critical angle, we only get reflection. So what we would get is an increase in that angle there. Take that annoying little arrow with us. We would get only reflection and no refraction. We call this idea total internal reflection, and it happens when the angle of incidence here is bigger than that critical angle that we just saw a minute ago. Any angle above that critical angle will get reflection only, no refraction, and we call that total internal reflection. Now, if you're doing the higher tier, there is a certain equation that you need to know, and that equation can be found on the equation sheet that's actually given to you in the exam. And I've just taken a little snippet from that equation sheet, and it looks like this. It says that refractive index equals 1 divided by sine c. Now, this is going to require to have some reasonable math skills to be able to do this, but I'll take you through it now anyway. Here's one example of where you might use this particular formula or this particular equation. So we have over here, example number 1, we have a critical angle of 42 degrees. So our angle at which this is happening, our critical angle, is 42 degrees, and we want to find out our refractive index. So we can use this formula here to do that. So let's substitute in the numbers into the formula. So we have refractive index equals 1 over sine c. C is our critical angle, which it tells you here, and in this example it's 42. So it's 1 over sine of 42. So if I work out sine 42 on my calculator, it's just a simple case of putting in 42 and pressing sine. or some calculators you have to do it the other way around, but if I find out sine 42 from my calculator, I believe it's 0.669, and to work out our critical work out our refractive index, we just do 1 over 0.669, which I believe is 1.49. Okay, so this is the refractive index of the material that we have here, based on the idea that we have a critical angle of 42 degrees. There you go, just tidied that up a bit because you need to be able to read it, plus I need to be able to get an example number 2. Now example number 2 is a little bit more challenging and it requires slightly higher maths skills. You need to be able to rearrange a formula. Now if you're not very good at that, don't worry, we can use a formula triangle. This formula triangle won't be given to you, but this formula triangle is basically this equation, I should say, not formula, this equation here in the form of a triangle, so that you can rearrange if you need to. So I'm just going to get rid of this so I've got more space, and what we have here is the refractive index is given to us as 1.59, and we want to work out the critical angle. So again, if we substitute into our formula, we have the refractive index, in this case is 1.59, equals 1 over sine of our critical angle. Now we haven't been given the critical angle, so we've got to work that out. Now we need to make sine C the subject of our equation. So what we do is we use our formula triangle down here. I'm using the word formula and equation interchangeably, but I think you know what I mean. So we use this triangle over here, and we want sine C to be the subject. So the way we do this is what we want, sine C. So that will give us 1 over the refractive index. So we can rearrange this. We have sine of our critical angle is 1 divided by 1.59, the 1.59 having been given to us, and if we work out 1 divided by 1.59, we get 0.628. So that means sine of a certain angle, sine of our critical angle, is 0.628. But what is that angle? This is where we need to use a special button on the calculator, and it looks a bit like this. So you've got sine to the -1. We use that to work out which angle has a sine of this value of 0.628. So if you're good at maths, you probably know how to do this, but basically we have a button on the calculator that either says INV, and then you can press sine, and that will give you access to sine to the -1. Sometimes you have second, the button that says second, and it will give you access to sine to the -1. So all we do is we press 0.628 into our calculator, tap sine to the -1, and we'll get an answer of 38.90. So this is our critical angle. We've calculated the critical angle by rearranging this formula here, which is in this case 38.90. So everything that we've got on the right hand side here, where it says higher, this is all required for the higher tier. Everything on the left hand side, the idea of critical angles and total internal reflection, is on the foundation paper, but you do need to know this for both papers. Now what we're going to look at next is an application of the use of total internal reflection. And total internal reflection is used in optical fibers, and the type of instrument that uses, or one type of instrument that uses optical fibers, is what we call an endoscope. And an endoscope is used to look inside the body without having to do any surgery. So an endoscope looks a little something like this. So here it is. This is what it looks like in real life. We've got the long optical fibers down here. We've got an eyepiece that the person, the surgeon or whoever's looking, can look into. And here we have another cable that supplies the light and one or two other things. But what we can do is look at this diagram that I've drawn, a slightly simplified version of that endoscope, and see what's actually going on inside. So if I magnified a small part of it there and look to see what was going on, here's our optical fiber, and what we can see is that the light rays that are used, that are supplied by the extra cable here, the light rays go in and they use this idea of total internal reflection. So the light ray will pass into the optical fiber like so and bounce off the inside of the material as they go along, and in this way we can have the endoscope being quite flexible and allowing light to actually travel through changing direction, and it can actually be used to see what's going on inside the body. What we do with these endoscopes is we look inside the body and we can see any problems that there might be, and it stops us from having to actually do any surgery, which would take quite a long time to recover from. This just takes a very short amount of time to recover from being examined using one of these. The last thing I want to look at quickly is this idea of lasers, and this has just been sort of tagged onto this topic for some reason, but basically lasers are intense and focused light, monochromatic light, which means light of just one wavelength or just one color, but it's very intense and very focused, and it can be used with our endoscope as we've described here. So we can have not only light going through here, but we can have laser light that goes through there as well, and it can be used for what we call cauterizing, which is sealing off damaged blood vessels. It can be used for cutting as well, not necessarily inside the body, but also applications outside the body. It can be used for burning. It can be used for something like laser eye surgery, which is a way of burning away a very thin layer of the lens in the eye, which can correct defective vision. You can imagine that in the exam they might like to combine this idea, laser eye surgery, the idea of using lasers that can burn, to changing the shape of a lens, and maybe you applying that to how that changes the way light rays are refracted in the eye to correct vision. But that's just me just having a guess. That's not anything that I know about the exam. Anyway, that's me done for this video for now. Thanks for watching, and I'll see you again soon.